Hey everybody, this is Angelo Costante, and we will be reviewing Chapter 2. Chapter 2 consists of 6 lessons. It is 2.1, function, 2.2, graph of a function, 2.3, properties of a function, 2.4, library of functions, a piecewise function, 2.5, graphing techniques, transformations, and lastly 2.6, mathematical modeling.
Chapter 2.2 is all about finding points in the domain of the graph numerically. To solve for a in example 1, first plug the points into the equation and simplify. If the two sides are equal to each other, then it is a point, but if they are not equal to each other, then it's not a point. For b, all you must do is plug negative 2 into x and simplify. Solving for c is only a little harder. Plug negative 1 into y and simplify, then factor out an x. Once you have done that, make them equal to 0 and solve. To solve for e, all you gotta do is factor and make it equal to 0 to find the x-intercepts. And lastly, solving for f, all you must do is make the x's equal to 0 to find the y-intercept. Chapter 2.3 is all about finding max and mins when an interval is increasing and decreasing, as well as find the average rate of change. Some terminology that is needed to understand this chapter is absolute extrema, local extrema, constant, open interval, closed interval, and average rate of change. You're probably wondering to yourself, what do they even mean? Well, absolute extrema is the highest and lowest points in the graph, while local extrema are the max and mins. A common mistake in determining whether there is an absolute extrema is to say there is an absolute extrema when the graph includes all real numbers, meaning the lines go on forever, so there is no absolute max or min. A good way to remember is if there is an absolute, there will always be a local extrema, but if local, there may not always be an absolute extrema. Now that we have that, constant is when a graph slope increases or decreases at a regular interval. Open interval does not include the point, while closed interval does include the point. And the average rate of change is the slope of a graph. The first step to finding the average rate of change is to plug in the x's it gives you into the equation. Doing this will allow you to find the y. Repeat this with the second x. Once you find both points, plug it into the average rate of change formula to find the slope. Some questions will go the extra step, asking you to find the equation for the secant line. To do this, choose one of the 2 points and plug it into the point-slope formula. Once this is done, simplify it and it will give you the equation.
With chapter 2.5, which has to do with transformations on a graph. So first we have transformations. So transformations are any alterations that are done to a graph. And mostly these functions are going to look like this. So it's going to say a to the f of bx minus h plus k. So of course these signs, the negative and the positive aren't always there, but this is just an example. So a is a vertical stretch or compress. That basically means it's going to make the graph bigger or smaller on the vertical axis, and that's going to be the x-axis. Next we have b, which is a horizontal stretch or compression. That's going to move the graph bigger or smaller this ways, up and down, because it's the y-axis. Then we have our h, which is a horizontal shift, which basically means it's going to move the graph up or down only on the y-axis. Then we have k, which is a vertical shift on the x-axis, which basically means left to right. So when we have our reflections, so reflections happen when there's a negative in front of our f, which would be right here. And that would be a reflection over the x-axis, meaning it's once again a vertical transformation. And then we have f of negative x, which would go somewhere right here. And that's going to be a reflection over our y-axis, meaning it's a horizontal transformation. So those are our terms. Let's get right to our example. All right, on to example number 1. So let's read the problem out loud and then we'll solve. So graph the function, then find the domain and range. Well, seems pretty simple. But what we have to first remember is we have to look at our transformation. So first things first, let's look at our transformations from left to right. We first have this negative in front of our parentheses. That means it's going to be a vertical reflection. So what does a vertical mean? Let's remind ourselves again. Whenever it's vertical, it affects our x. So let's put x equals v. And whenever it's horizontal, that affects our y. So I'll put y equals h. This is just a little bubble to remind ourselves which reflection is which. So let's label them once again. So we have a reflection across our x-axis because it's a vertical. Next, let's see what else we have. We have x plus 1. Whenever you're trying to find these transformations, you're always going to equal the set of parentheses, whatever's in the parentheses, equal to 0. So in this case, we have x plus 1. So we're going to set x plus 1 equal to 0. So doing standard operations, we're going to subtract 1 from each side, and we're going to result with x equals negative 1. Essentially, what does that mean? That just means it's going to go left 1. So in this case, because it's a negative, it's going to go down. So we're going to go down 1 unit. So now it's important not to bypass this cube we have over here. Because what does that cube represent? That's basically going to help us find our parent graph. And that's one error that people usually don't see. They're going to go straight to the graph, but what they have to realize is they have to draw out their parent graph first in order to see the transformations. So let's draw our parent graph. Logically, we should always do the biggest transformations, and that's usually going to be our reflections or our stretches or compressions. So let's look back at our list. We have a reflection going left, and then we're going down. Let's think about it. What's the most effective way to do this problem? That's right. It would be to reflect over our x-axis first. So let's go ahead and do that. So this is what our graph is going to look like, reflected over our x-axis. Let's go ahead and color code that. So red is going to be a reflection. After a reflection, now we can go wherever we want. It's kind of like a Pedma's rule. So now we can go up, we can go down, we can go left, or we can go right. So just because we're going sequential, let's go to left 1 unit. So when we're going left, we just skip over 1 unit to the left. So let's go ahead and do that right now. So now I've done our left 1 unit transformation in blue. So let's go to color code that. So now we have one more transformation left, and then it's going to be going down 1 unit. So it's a little hard to see, but this one's going to be in black, and this is our final transformation right here. So it's going to be right here. So usually, to not upset Miss Man, we're going to erase all of our other transformations and just leave our final transformation. So that's going to look a little something like this. Alright, so here's our final graph. And so we have graph the function, so let's put a little check mark by that. Now what do we have to do? We have to find the domain and range. So let's do a little refresher. Domain is going to be our x-axis, or mostly our x values. And then our range is going to be our y values. Alright, so our domain is going to be found from looking from left to right, because once again, that's our x-axis. So we see an arrow here, and we see an arrow here, meaning that they're going to continue on for infinity, but we're going to do the lesser value first. So this is continuously heading towards negative infinity, and continuously going towards positive infinity. So that's our domain. Next, let's look at our range. So range is going up to down. So once again, we see these arrows, and that's basically means it's going to go on to infinity forever, and negative infinity forever. So let's write our lesser value, and that's going to be negative infinity, all the way to its highest value, which is going to be infinity. Alright, on to section 2.6 and our first hard problem. So it says, Santa's elves are making a storage unit for extra toy parts. If each side is 3 feet in length, and the open configuration doubles, the available area that parts can be stored go from 9 feet to 18 feet. Hinges will be added to allow for easy access to the parts. Alright, so looking at this from a bird's eye view, we have a rectangle, and we also have a triangle at the top. So it kind of looks like a little house, if you want to imagine it like that. And now let's do the dimensions, just so we get a better understanding. Now that we visualized, let's go on to our first step of the problem. That's going to be to solve the area. Alright, on to part A of our problem. So let's go ahead and read it out loud. It says, build a model that expresses the area A of the toy box shown as a function of the distance x between 2 parallel sides. Basically what that's saying is find the combined area of both the rectangle and the triangle on top. So for a rectangle, it's fairly easy. It's just base times height. And in this case, it's going to be x times 3. So x times 3 is 3x. And that's going to be our combined rectangle area. Next up, we have the area of our triangle. So in this case, we actually have 2 variables, and that's going to be h, and that's going to be x. We're going to have to solve for one of the variables. So let's go ahead and check this out. So we have 1/2 times base times height. In that case, it's going to be height, and we have our base. So let's go ahead and draw this triangle right here. We're going to be given h3, and because this splits right down the middle, it's going to be half of x, which is actually x over 2. And we're going to get our measurements of the triangle. So now in order to solve for one of the variables, we have to use the Pythagorean theorem. That's going to be a squared plus b squared equals c squared. Let's go ahead and plug them in. So we have a squared, which is one of the sides, so let's say h. So we have h squared, plus b squared, which is another side. It's going to be x over 2, once again squared, is equal to the hypotenuse. In this case, it's going to be 3, so 3 squared. So we're going to be left with h squared, x squared over 4 equals 9. Now, in order to solve this, because we do have 2 variables, we're going to have to use the quadratic formula. So now we're left with the square root of 9 minus x squared over 4 equals h squared. Now, in order to isolate the variable, which it would be h in this case, we would have to square root both sides, and then that's where we implement the quadratic formula. In the end, using some more math magic, we get the square root of 36 over 4 minus x squared over 4 equals h. So now, just to simplify that even more, we can factor out a 1/2 out of each side. In that case, we get 1/2 to the square root of 36 minus x squared. Alright, so now that we know that equals h, we can plug that in to our original equation for the area of the triangle, which was 1/2 times base times height. So now we plug in 1/2, base in this case was x, times the height, and we already found the height here, so we plug that in, and now we have to find the combined area. So the combined area would be the area of the triangle, which is 3x, plus the area of the triangle, which would be 1/2 x times 1/2 to the square root of 36 minus x squared. So when you multiply that out, you would get 1/4 x to the square root of 36 minus x squared, and don't forget to add that 3x. So now that is the combined area of both the rectangle and the triangle.
That'll be all. We hope this helped. Best of luck on the final and happy holidays.